This is problem 30 from chapter 14. The 30-pound box A is released from rest and slides down along the smooth ramp onto the surface of a cart. If the cart is prevented from moving, determine the distance S from the end of the cart to where the box stops. The coefficient of kinetic friction between the cart and the box is 0.6. So we're going to use the equation that we have here, which relates the potential energy or the potential energies in this case, the kinetic energy, and the work. There are no springs in this problem, so I did not copy down the elastic potential energy. And the height of the box is changing, so we do have a change in gravitational potential energy. We're looking for the distance S when the box stops moving, so we're going to go from point A, it says box A, but we'll say point A is here, to point C. So I'm going to make this the velocity at point A at the top of the ramp. This is height A, and this is the velocity at point C and the height at point C. But the box is released from rest, so the initial velocity is equal to 0, and we're looking at the distance from the end of the cart when the box stops moving, so the velocity at point C is equal to 0. So this is 0, and this is 0. And I could also say that the height at point C is 0, so I could make that 0 also, in which case the height at point A is 4 feet. So that makes things nice. And then all I have left to do is determine the work done by forces other than gravity. One thing I wanted to mention is that it says the box slides onto a cart, but the cart is prevented from moving. So in this case, it doesn't really matter that it's a cart because the cart can't go anywhere. So I can calculate the initial gravitational potential energy, but I'm going to save that for later. So I'm going to focus on the work done by other forces. This is U. The way they write it here is U as you go from point 1 to point 2. So for us, that would be as we go from A to C. If you wanted to, you could find the work as you go from A to B, and then as you go from B to C, you could use this relationship twice, with the initial being at point A and the final being at point B the first time you use the equation. Then you could make the initial point B and the final point C the second time you use the equation. Or you could just, as we're doing now, go from point A to point C all at once. What you do have to be careful of, though, is if you're going right from point A to point C, is that some of the forces that you have may not be acting on the box the whole time. So the ramp itself is smooth. So while the box is on the ramp, there is no friction. So we have a smooth ramp, so no friction when you're on the ramp. But then afterwards, when you're going from point B to point C, you do have friction. And that would be the only force that we need to consider when we calculate the work done. If I draw a free body diagram when the box is on the ramp, I have a normal force and I have a force of gravity. The normal force is perpendicular to the displacement at all points on the ramp, so the normal force does not do any work, and the force of gravity we're already accounting for. When the box is on the cart, we have, again, a normal force, but it is perpendicular to the displacement, so it does no work. We have a force of gravity acting downward, which we do not need to consider because we already took it into account when we did the gravitational potential energy. And I have a force of kinetic friction, which is going in the opposite direction of the displacement. So when I do the dot product, I will get a negative sign. So I'm going to put that negative sign in, and then this is the magnitude of the force of kinetic friction, and the magnitude of dr is ds. But this force of kinetic friction only acts when I go from point B to point C, so my limits of integration here should be from point B to point C. And I would just like to say, we're going to start here, and we're going to call this 0. And then we're going to go here to this location, which would be 10 minus s. So that's the coordinate system I'm going to use for this. It will allow me to find the distance s, and it just makes it easier to say we're starting here at 0, we're going in the positive direction, we end at 10 minus s, and it's not going to change anything to set it up that way. I need to find the force of kinetic friction. This is equal to the coefficient of kinetic friction, which I know, times the normal force, and maybe you can see from my free body diagram here that the only forces acting in the vertical direction are the normal force and the force of gravity, and there's no acceleration in the normal direction, and so the normal force is equal to 30 pounds. So this is the force of kinetic friction is equal to the coefficient of kinetic friction times the normal force, and the normal force is equal to 30 pounds, and the coefficient of kinetic friction is equal to 0.6. So this is 0.6 times 30. And then I can take that and put it in here. The force of friction is actually constant, so it could come outside the integral. So when I integrate with respect to s, I get 0.6 times 30 just times s as I go from 0 to 10 minus s. And so I guess it is slightly confusing to have an s here and a 10 minus s there, but we've seen worse. Okay, so then I get minus 180 plus 18s, but this is just the work done, so that needs to go back into my equation here. I still need to calculate the initial gravitational potential energy. M times G is 30 pounds. The initial height is 4, so that's 30 times 4 minus 180 plus 18s is equal to the side of the equation, which is just 0. And then I solve for s, and I get s is equal to positive 180 minus 30 times 4, which is 120, divided by 18, and if I did everything correctly, that should give us 3.33 feet. So that checks out, and that concludes problem 30.